Okay, so we're beginning to look at non-uniform circular motion. So a quick review of the difference between tangential components and radial components. Remember, when we're looking at the position of an object in a circle, we are interested in what kind of vectors are directed radially. That's this direction along the axis, and tangentially, which is this way. Okay, radial, tangential. All right. So things that can typically be tangential, we often look at tangential velocity. Okay. For circular motion, whether uniform or non-uniform, we're going to look at radial speed generally being 0, because if things were along the radial, if moving radially, the thing would be spiraling in or out, and we want things to stay in stable circles right now. Remember, we also have things like tangential acceleration, and we also have a tangential net force. Radially, we do have a radial acceleration, however, we most normally call it centripetal acceleration, although both words can be interchangeable. And we can have a net force radially, but we also tend to refer to that as the centripetal force. Okay. Fictitious forces, this is something that sometimes comes up. Remember, we talked about these before. Things that appear to have magic forces that appear from nowhere are what we call fictitious forces. Things that, when we view things in a non-inertial reference frame, in other words, we're not looking from a rest point of view. So the example here in the screen, you're on a bus watching a ball, and if you're just looking at the ball and then suddenly the ball rolls to the front, it looks like something magic just happened and the ball rolls to the front. But if you move outside the bus and you're standing relative to the ground, where the ground is definitely inertial, the bus is not inertial because obviously it had been moving forward. We couldn't see that just on the bus in the picture of just, oh, we're sitting on the bus staring at a ball. But standing outside the bus, we can see the bus is moving forward, and the ball and everything's moving forward, but suddenly the bus driver steps on the brakes. You have enough friction between you and the seat to keep you in place. The bus slows down, but the ball doesn't have enough friction, and it's an object in motion trying to stay in motion. It appears and it rolls to the front of the bus because it's trying to stay at the same speed that it was going beforehand relative to the ground. So those imaginary forces seem to exist. Oops. So we're looking at wanting to see in circular motion, the fictitious force that most people often talk about is something called the centrifugal or centrifugal force. Okay. This is a force that gives the appearance that things are being thrown to the outside. While objects may feel like they're being thrown, there is actually no known force that's actually pushing things toward the outside of the circle. We definitely, as we analyze all the forces acting on things, we find all kinds of things pulling into the center of the circle. Sometimes the tension of a string, the friction on a car. Pulling in keeps things in circles. Pushing out actually doesn't. But when you are there, you feel like you're being thrown out, as in the zero gravity ride there. So that is a fictitious force. Okay, now quick review. Uniform circular motion. This is a constant speed motion where you see that tangential velocity is constant. Again, radial is always going to be 0. So velocity is constant, which means angular velocity is constant. Angular acceleration is 0. We are not speeding up or slowing down around the circle. So tangential acceleration is 0. In this case, our total acceleration would just be equal to centripetal because tangential is 0, and so the net force is just the centripetal force. But now if we move into non-uniform circular motion, where tangential velocity now is not constant, I can be speeding up or slowing down. Again, we will always keep radial 0. Omega, or angular velocity, is also not constant. Alpha is not 0. Okay, we will most likely keep that constant. I have not seen any problems that don't have that constant at this point in non-uniform circular motion, but a lot of times we look at just certain little instances. Now, total acceleration is still the square root of AC squared plus AT squared centripetal plus tangential. And again, that comes from looking at the triangle here. You can see the tangential acceleration here going tangential to the circle, and the radial acceleration going along the radius. And if you imagine drawing this radial acceleration at the end of the tangential so that we can complete this triangle here, okay, where this is AR, which is the same thing as AC. You can see that we form the triangle, and this equation for A total up here just comes from Pythagorean theorem, okay, where this A in the middle is A total. We get a similar relationship with centripetal force and tangential force. Again, this net force, this is the same thing as centripetal force pointing along the radius here. And so you can see here, here's where I could also draw the centripetal force or the radial force and form the triangle. That forms this Pythagorean theorem thing right there. Okay. Let's go on and talk about finding minimum speed. I want to talk about vertical loops because you know, if you've ever played with Hot Wheels cars and racetracks, you know that sometimes if the car's not going fast enough, as we look at it going around the loop here, right, it tends to go faster at the bottom and it gets slower as it goes to the top. And if I'm not going fast enough at the top, the thing could actually fall off the track and fall back down and crash. So we want to make sure we have enough speed at the top and figure out what that speed needs to be to keep things going around in a tight circle. I'm going to look at two free body diagrams. First, analyzing the forces at the bottom. Imagine this is the biker at the bottom. Okay, while he's at the bottom of the loop, he has two forces. He has gravity, and he has normal force. Now, normal force is actually the larger force because he's in a circle, and we know that centripetal force, if things are moving in a circle, centripetal force definitely points toward the center. So in order to make these two forces point towards the center, normal force must be larger. And so the equation I have is centripetal force equals normal force minus gravitational force. All right, now if I look at the forces at the top, again, here's, imagine this is the motorcyclist at the top. Now if I look at my forces, I still always have gravity pulling straight down. But now, because I'm at the top, the loop is above me, and I actually have normal force also pointing downwards now as well. And so this equation now looks like centripetal force equals Fg plus normal force, because normal force is now pointing down. Now, if I'm looking at minimum speed, just enough to get around the top, the impression is that right as we get to the top, I'm on the verge of losing contact with the track, but not quite just yet, you know, enough to make it around. So if I'm on the verge of losing contact, this means that normal force is going to go to 0. So if normal force goes to 0, what this means is that now that my centripetal force is just going to be equal to Fg, oops, sorry about that, tried to get an eraser, okay, it's just going to be equal to Fg because now Fn is going to 0, and if I expand this, I've got mv squared over r is going to equal to mg. You will notice, of course, that the m's cancel. And if I solve for v, v is going to equal the square root of gr, or what I like to call the square root of gr, and this is known as the minimum speed needed. Okay, so v equals square root of gr, minimum speed, to keep from losing contact around the top of the circle. All right. So let's look at a couple more examples. Here I have a car going over a speed bump or some sort of circle. It says an out-of-gas car rolling over the top. I'm basically trying to get rid of any sort of engine things that are going on here. So what I want to look at, again, this time the circle towards the middle is pointing downish. So in order to keep a centripetal force pointing toward the middle, I know that Fg has to be the bigger force. So when they want to know which of the forces is bigger, this lowercase n is normal force. Fg has to be bigger than the normal force so that I can make Fc equals Fg minus the normal force. Okay, that's just a simple problem trying to demonstrate always, look at the circle and find out where the middle is. So we know that's the direction of centripetal force. Okay, now in this case, this is a true story. My husband used to put our children in blankets and swing them around in vertical circles. Mary Ellen loved this. Some of the other kids didn't so much, but we want to know the minimum speed that Mary Ellen must have at the top of the circle to just make it around without falling out of the blanket. Well, we just saw a couple of slides ago that minimum speed was equal to square root of GR. Okay, and if I look at, we know G is 9.8 and R is 1.5. Forgot the decimal. Okay, and we put that in and calculate it, you should get 3.83 meters per second. Okay, if my husband spins Mary Ellen around so that the speed at the top of the motion is 5 meters per second, so now I'm not looking at minimum speed, I want to find the normal force. All right, so pretend this dot, this is Mary Ellen, okay? When she's at the top of the circle, I have gravity, and I have normal force, okay? And now we're not at minimum speed, so normal force is not going to 0. Now both forces are pointing toward the center of the circle, so we know that Fc is going to be equal to Fn plus Fg. If I expand, I have mv squared over r is going to equal Fn plus mg. My goal is normal force, so I'm going to solve for Fn, mv squared over r, minus mg equals normal force. All right, so substituting numbers in. All right, Mary Ellen is 5 kilograms. Her speed was 5 meters per second, so we'll have 5 squared. The radius, I believe, was 1.5 minus 5 times 9.8. And when I put that all together, I get a normal force of 34.3333 newtons. Alrighty. So now I want to look at a problem where what if I'm not straight at the top and straight at the bottom? What if I'm off-centered a little bit and the problem suddenly becomes a little bit more complicated? I'm going to make a quick list of givens. I have a 2-kilogram marble, not 2 kilograms, 2 grams. So if I convert this to kilograms, 0.002 kilograms is rolling around a radius of 20 centimeters. That'll be 0.2 meters. And the marble's at a location of 30 degrees from the vertical. It's determined that it has a speed, this would be tangential speed, by the way, of 3.05 meters per second. We want the force exerted on the marble by the track. So force from the track, that is essentially asking, what is my normal force? Now if I look at a free body diagram of the marble, I have the normal force from the track pointing straight in toward the middle. It's always perpendicular to the surface. However, gravity at this point is pulling straight down. Okay, now what do? These things are not nicely aligned. This is where we go back to kind of a tipped axis thing, where here is I will draw a tangential piece. Sorry, that's a radial piece, because that's along the radius. A radial piece. The tangential piece should be tangent. Okay, this is my tangential axis here. And now you see normal force is along the radial axis, so what I want to actually look at are components of gravity here. Okay, so this would be Fg tangential, and this piece here would be Fg radial. Hang on, I feel like I need to move this red Fg someplace else, over here perhaps. Let me draw in this triangle. Okay, so Fg radial. All right, now the things that I'm seeing, the equations that I'm looking at, I see that pointing along the radius are Fn and Fgr. So if I look at my radial net force, which is centripetal force, I have Fn plus Fgr. If I look along my tangential, I have a net force tangential would just be equal to Fgt. Now the real big question is this 30-degree angle right here. Where is that inside this triangle? So I'm going to look at some geometry here. I'm going to show it to you here in the video, and then I'm going to erase it. So I'm looking at this vertical line here through the vertical, and this vertical line through Fg, and then I'm going to look at the radial line here. If that is 30 degrees, I also know that this has to be 30 degrees. All right, and if this is 30 degrees, I also know then up here, because of the 90-degree angle, this angle here has to be 60, and this is 90, which means this one down here has to be 30 degrees. Okay, that's a big mess. I'm going to undo a whole bunch of that now that you see it, and just label this angle here as 30 degrees. Remember, you need to be able to perform these geometries to know where angles are. Okay, so now that we know where the 30-degree angle is, I'm going to continue to expand my equations. Fc is mv squared over r. Normal force is just normal force. And Fgr this time is going to be mg cosine 30 degrees. Net force tangentially, if I expand this, this would be mass times tangential acceleration, and Fg would be mg sine 30 degrees for the tangential component. Now, this just asked me to solve for normal force, determine the force exerted on the marble. So I think I can get that straight out of just the radial equation here. So if I solve for normal force, I have mv squared over r minus mg cosine 30 degrees equals Fn. And Fn equals, let me just pop in some numbers real quick. So we have 0.002 times 3.05 quantity squared, all divided by 0.2 minus 0.002 times 9.8 times the cosine of 30 degrees. And when you put all that in, I get a value of 0.0761 newtons for the normal force. Okay, now in this example, we're looking at some teenage boys going over a speed bump, okay, in a car. All right, so the idea is that sometimes when we go over speed bumps, we discover that we can catch air. Now, the free body diagram on the car looks like this. There's gravity and normal force. In this case, gravity has to be the bigger force because, again, it is pointing toward the middle. So we know that Fc has to be equal to Fg minus Fn. But if you are catching air, that means you are on the verge of losing contact, which means your normal force is going to 0. So if your normal force goes to 0, and we're looking at the minimum speed at which this can happen, I'm back down to mv squared over r equals mg, and if I quickly cancel out the masses here, I get back down to v equals the square root of gr. And this is cool because what we find is whether the object is actually traveling on the inside of a circle, as on the track of a roller coaster or loop-de-loop, or whether it's on the outside of the circle, my equation ends up being the same. Minimum speed is still square root of g regardless. All right, let's look at Andy driving his car. A couple things I noticed right away in reading this. They give me the diameter, constant trick. I think in physics problems, you need to remember we need the radius, which is only going to be 100 meters. All right. Ooh, I'm given some interesting things. Initial velocity is 0 because it starts from rest. Speeds up at a steady, I've got this looks like a tangential acceleration, 1.5 meters per second squared. How long after starting? How long? It's asking me for time. Is the magnitude of centripetal acceleration equal to tangential? So I know centripetal acceleration is equal to tangential. Now my train of thought here, when I'm looking at time, a lot of times I'm thinking of kinematics, and I've got initial velocity, I've got acceleration, I've got time. What I really need is final velocity. If I get that, I can head into a lovely equation, which we all know and love, that looks like final velocity equals initial velocity plus acceleration times time, where initial velocity is 0. So if I get final velocity, I've got the time very easily. So how am I going to get final velocity? I would look at the equation for centripetal acceleration. Since we know centripetal acceleration, we know this is going to be v squared over r. And at the point that these are equal, that will be my final velocity. So that v will be final velocity. So if I can solve for v, you can see it's just going to be the square root of centripetal acceleration r. So v is going to be the square root of 1.5 times 100. And v ends up being equal to, hang on just a second, I have it here, 12.2474 meters per second. Now if I go back over to my other equation solving for time, Vf over A equals T, I can quickly calculate the time to be 12.2474 divided by 1.5, and the time should be 8.1650 seconds. Okay. Incidentally, I know it doesn't matter in this problem, but this time, since we were using tangential velocities in this equation, these are tangential velocities, this has to be tangential acceleration in order to make this equation work. However, tangential and centripetal are the same, so that's not entirely clear, but I wanted to point that out. Okay, now what is the total acceleration of Andy's car? Keep in mind that while he's driving in a circle, right, we have that tangential acceleration here, which we were told was 1.5 meters per second squared. We have the centripetal acceleration here, which we were also told was 1.5 meters per second squared. So if I take the centripetal and I redraw it perpendicular here so I can form the triangle, I can see here this is a total acceleration. Let me relabel this. This is centripetal acceleration. So you can see it forms a triangle. So in order to find a total squared, I'm going to use centripetal squared plus tangential acceleration squared. So a total should be equal to the square root of 1.5 squared plus 1.5 squared. And a total we find to be 2.1213 meters per second squared. Now it also wants the angle, okay? So from the tangential, it says measured from the tangent line, AT is tangent, so it's actually asking for this angle theta. You probably already can tell what it is, but just in case, I will redraw the triangle a little bit, just so you can see this is going to be 1.5 meters per second squared, 1.5 meters per second squared. Here's a total, 2.1213 meters per second squared. And we are looking for this theta here, where the 90-degree angle is up there. So this is just going to be, just in case you don't see this, a tangent of theta is going to be opposite over adjacent. Opposite is 1.5, adjacent is 1.5. We're going to get the 1, and when we inverse tangent that, we're going to get a 45-degree angle, which if you didn't pick that up because the sides were equal, well, then you can do the math. Okay, now if Andy's car has a mass of 200 kilograms, what is the total net force acting on the car? In this case, net force is going to be mass times total acceleration, because they wanted the total net force. So we've got 200 times 2.1213, and when you multiply those together, you get 424.2601 newtons. And there is our total net force. All right, now based on all of that, you can now do all the problems in circular motion. Good luck. There's a whole bunch of non-uniform circular motion ones to give you lots of practice.